single word I would use to characterize FOSS is revolutionary. If it can be used and utilized and implemented effectively, I believe it can really revolutionize the way we do our business in aerospace.
Game changer. Fiber optics is a game changer because we can lay a line of fiber in any orientation on that structure and we get a continuous measurement of strain. It's a game changer because it gives designers real-time information which they never had before.
These are all the individual fiber optic sensors on the wing, and then these are the individual strain values.
You have deeper insight into how a structure performs, not only in operation, but all the way through its life cycle. From the development of a structure, as you get it ground tested, as you transition into a flight environment, as you get to the end of the life cycle when you're trying to determine how much life is really remaining in the structure. FOSS can save time on your schedule for installing sensors. It can give you greater insight and much more spatial fidelity in your measurement system than ever before.
We have given the designers a new tool within their toolbox to use to validate their models.
The state-of-the-art technology in fiber optic sensing is something we've been advancing in order to be able to allow a wing in flight to maintain the optimal configuration. And the first step towards wing shape control is knowing what the position or the displacement or deformations of that wing is as they traverse through the air and they're subjected to wind gusts and atmospheric turbulence and things like that. I think the genesis of FOSS came about as a result of working with conventional technology. What I mean by that is strain gauge technology in particular and thermocouples. Strain gauges measure strain and thermocouples measure temperature.
This is the conventional way of doing health monitoring for structures. Each one of these connectors is the termination for each one of these go packages that you see mounted on this panel. And each of these go packages, these conventional strain gauges, have with them the associated wires that have to be soldered on, it has to be prepared, they have to be terminated using various types of connectors. There's a lot of work involved in installing these conventional strain gauges. And with the strain gauges, they are only making point measurements. So wherever you see a go package, we are making that strain measurement at that one location.
Imagine having your arm have one measurement and you wouldn't be able to feel anything else around it. It's kind of limiting. Same thing structurally. You don't have a lot of insight into what's going on in the structure if you have a sensor every several feet. The FOSS technology allows you to have a sensor every quarter inch along the single optical fiber. That allows you to look more and more like a biological system.
Very lightweight, much easier to install, less complexity. 21 strain measurements, 1,400 strain measurements on a single fiber. For practical purposes, you can put as many of these fibers on your vehicle as you want or on your structure as you want without sacrificing the weight requirements.
Instead of using current and voltage and the resistance of that electroresistive strain gauge, now we're shining a light down this optical fiber.
And as that light propagates down the fiber, it comes in contact with what we call Bragg gratings. And these Bragg gratings are like translucent mirrors that reflect at very unique wavelengths. These unique wavelengths that are reflected are actually sampled and measured.
Those changes in wavelength are what we calibrate to engineering parameters. One of the powerful aspects of FOSS is that it's not only the number of measurands that you can monitor, measurand being strain or temperature, basic engineering parameters that we use to quantify a structure's performance. It could also measure liquid level, magnetic field, three-dimensional shape.
As I apply pressure on this test article, we can see how the shape is changing as well as the intensity of the strain being felt by the test article. What we have here is the demonstration of the liquid level sensing technology. And what we're able to do is use the fiber optic sensors to monitor the different absorption rates of the liquid and the air to determine where is the boundary between liquid and air. Here we have a demonstration of our hybrid fiber optic system. With this, we're able to get our quarter-inch spatial resolution at up to 100 samples a second. And at strategic places, we can place a strong grating, that we call it, that allows us to acquire strain measurements at up to 5 kilohertz.
I think commercial applications are really endless. I mean, the more that we explore interests in different realms, we understand that there's really a role for FOSS in ways that we never imagined to begin with.
In 20 years, the hope is that we would see this on commercially available aircrafts, we would see it on expendable launch vehicles as health management systems for ELVs. Another big area is oil and gas, monitoring the drill head on a downhole rig, being able to look at what the status is on the holding tanks.
Liquid level inside of a tank, in cryogenic propellants, or in any kind of fluid through pipes.
And the list just goes on and on.
I think what excites me most about FOSS is seeing the light go on in people's eyes, or the light bulb actually shows up above people's heads when you start to describe for the first time the capability of the technology. This could really change the way they do business. This could save a lot of time on their schedule, because now they only have one system that can perform all these measurements. So for me, it's seeing that epiphany, seeing that actually develop, and seeing the application potential, I think, has really been rewarding. You know, it does go almost anywhere into various places where you're monitoring structural response. So to see that happen is pretty rewarding and exciting.